Hello and welcome to this tech tip from Will. In this tech tip I will look at DHCP Failover for Windows Server 2012 and Windows Server 2012 R2. I will start by explaining what DHCP Failover is. Next, I will provide an overview of DHCP Failover and will look at the requirements for implementing it as well as the different methods of configuring it. And later, I will demonstrate how to set up and implement DHCP Failover using two of my Windows Server 2012 R2 servers. Before I begin this tech tip, it is important to note that this lesson is not aimed at beginners. DHCP Failover is an advanced feature. For that reason, it would be advantageous if you already have a relatively good understanding of DHCP and DHCP in Windows servers. Throughout this tech tip, I will be using a lot of Windows DHCP terminology. You will find this tech tip much easier to follow if you are already familiar with DHCP scopes, leases, exclusions, reservations, and DHCP options. Any exposure to DHCP in earlier versions of Windows Server will be very beneficial. So let's get started. The first question you probably have is, what is DHCP Failover? DHCP Failover is a brand new feature to Windows Server 2012 and Windows Server 2012 R2. DHCP Failover, in a nutshell, is designed to make the DHCP service on your network highly available. But what exactly do I mean when I say highly available? The idea of high availability is to reduce downtime and keep the services on your network up and running for as long as possible without any interruption. High availability is usually achieved by identifying and removing single points of failure from your infrastructure. The most common way of eliminating single points of failure from your server infrastructure is to create what are called clusters. When you set up a server cluster, you will essentially have two or more servers perform the same task. That is, you would deploy two servers, Server 1 and Server 2. You would then install some kind of application or service that can be clustered onto both servers. Next, you will create the cluster. When the cluster is in place, if you were to make a change to the application on Server 1, the changes you make will be replicated over to Server 2. In other words, the applications on both servers are synchronized with one another. The benefit of this is that if one of the servers in the cluster were to fail, the surviving server can continue to provide the service alone, since it holds a fully synchronized, up-to-date copy of the application. As such, the only way the application or service will be made unavailable is if the entire cluster were to fail. Microsoft has worked very hard to ensure that the majority of their core networking services, including Active Directory and DNS, can be clustered and thus configured for high availability. However, until the release of Windows Server 2012, no such functionality existed for DHCP. Since high availability for DHCP is not available in Windows Server 2008 R2 and earlier releases of Windows, network administrators were forced to use workarounds to achieve some sort of high availability. The most common workaround by far was known as split scope. Split scope is possibly the closest you can get to high availability for DHCP prior to Windows Server 2012. Understand, although split scope does have its advantages, it is not a true high availability solution. Let me try to explain why. Split scope requires a minimum of 2 servers to work. On both servers, you would install a Windows Server operating system such as Windows Server 2008 R2. Next, you would install the DHCP server role. When the DHCP server role is installed, you can turn both of these servers into DHCP servers. When you install the role, a database is created locally on each server. This database stores all of the DHCP configuration data for that server, such as scopes, IP address leases, exclusions, reservations, and DHCP options. The problem, however, is that there was no way of getting these databases to communicate with one another. As such, both databases were completely unaware of the other's existence and believed that they were the only DHCP database on the network. Next, the administrator would have to create a DHCP scope. A scope is simply the range of IP addresses that are handed out by the DHCP server to client computers when they join the network. For instance, if I were to create a scope of 192.168.1.101 to 192.168.1.200, this would give me a total of 100 IP addresses that can be assigned to clients. The question is, where to place the scope? Do you create it on the first server or on the second server? A common error made by a lot of inexperienced technicians is to create the same scope on both DHCP servers, believing that if one of the servers were to fail, the surviving server can continue to provide IP addresses to clients. However, this is totally incorrect. Remember, prior to Windows Server 2012, the databases on the DHCP servers cannot communicate with one another. If you create the same scope on different servers, you essentially have 2 DHCP servers that are completely unaware of the other's existence, handing out the same IP addresses to different computers on the network. On TCP/IP networks, every computer must have its own unique IP address. If 2 computers on the same network are assigned the same IP address, neither device can participate on the network. The end result of this configuration is a complete collapse of network connectivity between your client computers. The only solution to this problem is to split the scope in 2 and create a different scope on each DHCP server, hence the name split scope. For instance, on one DHCP server, I could create a scope of 192.168.1.101 to 192.168.1.150, and on the other, a scope of 192.168.1.151 to 192.168.1.200. The end result is 2 scopes, each containing 50 IP addresses, on different DHCP servers. This is, of course, just a demonstration. You can make the scopes any size you choose, and they do not have to be evenly split. With split scope implemented, if one of the DHCP servers were to fail, you can rest assured that only a portion of your entire scope is taken down, and that the surviving DHCP server is still capable of serving IP addresses. Of course, depending on the size of your network and how you have chosen to split your scope, you could, in some cases, find that there aren't enough IP addresses to go around. This is why split scope is not considered a high availability solution. With Windows Server 2012 and Windows Server 2012 R2, Microsoft has made improvements to DHCP by introducing DHCP Failover, a brand new feature that makes DHCP a highly available service. So, what exactly are the requirements for DHCP Failover? DHCP Failover requires two servers to work, both of which must be running either Windows Server 2012 or Windows Server 2012 R2. It is worth noting that the operating systems used on the two servers do not have to be identical. You could, for instance, have one server running Windows Server 2012 and the other Windows Server 2012 R2. However, Microsoft does recommend that you match the operating systems if possible. Next, both servers will require the DHCP server role to be installed. Furthermore, both servers will require a static IP address. It is possible to implement DHCP Failover in either a workgroup or a domain environment. However, it is fair to say that, due to the costs of implementing DHCP Failover, it is far more likely to be found in domain environments. As such, all demonstrations of DHCP Failover that I will perform in this lesson will be done in a domain environment. Next, if you are using Windows Firewall, DHCP Failover requires that TCP port 647 be open on both servers to listen for failover messages. Finally, DHCP Failover requires that the clocks on your DHCP servers be synchronized to within 1 minute of one another. If the times on your servers are allowed to drift further apart than this, DHCP Failover will not work. Now that we are familiar with the requirements, how exactly does DHCP Failover work? To implement DHCP Failover, you must deploy two servers running either Windows Server 2012 or Windows Server 2012 R2. Both servers must have a network interface card with a static IP address and must have the DHCP server role installed. Just like earlier versions of Windows Server, when you install the role, a database is created locally on each server. Any DHCP configurations you make will be stored in the server's local database. However, this time, rather than create two smaller scopes, one on each server, you will instead create a single scope on one of the DHCP servers. For instance, let's take my earlier scope of 192.168.1.101 to 192.168.1.200. Rather than split the scope in two, I will create it whole on my first DHCP server. This may seem a little odd, but bear with me. There is a method to the madness. It is also worth noting that DHCP Failover only works on IPv4 scopes. You cannot configure DHCP Failover for IPv6 scopes. Once the scope has been created, the next step is to create what is called a failover relationship between the two servers. A failover relationship, in a nutshell, connects the two DHCP databases together. Each of the DHCP servers participating in the failover relationship are called partners. When the failover relationship is established, I am able to replicate the scope I created earlier with the other DHCP server. When replication occurs, absolutely everything configured within that scope, such as the leases, exclusions, reservations, and DHCP options, is synchronized with the partner server. It is worth noting at this point that you can have multiple scopes added to a single failover relationship if you wanted. The end result is two DHCP servers that both contain an identical copy of the DHCP scope in their local database. From this point on, when a change is made to DHCP, such as a client computer leasing an IP address, this change is updated on both partner servers. Since the two partners will replicate periodically, if one of the servers were to fail, the surviving DHCP server can continue servicing clients alone, since it has its own up-to-date copy of the database. One important point I would like to make is that a failover relationship can only have two partners. You cannot add more than two servers to any failover relationship. That being said, it is possible for a single DHCP server to have multiple failover relationships with different DHCP servers. For instance, let's say I were to add a third DHCP server to my network. Since I already have two partners in the current failover relationship, I cannot add this server to the relationship. However, I could instead create a completely separate scope on my new server and then create a new failover relationship with one of my existing servers. You can have up to 31 failover relationships on a single DHCP server. Just remember, there can only be two partners in any failover relationship. Now that we know how DHCP failover works, the next topic to discuss is DHCP failover modes. When you create a failover relationship between the two DHCP servers, you will have to choose a mode that determines how it works. The first mode, which is also the default, is load balancing mode. With load balancing mode, both partner servers in the failover relationship will work together to assign IP addresses to clients. That is, when a client computer boots up and requests an IP address, it can obtain an IP address from either one of the partner servers. If you opt for load balancing mode, Windows will, by default, distribute the workload between the partners evenly on a 50-50 ratio. That is, each partner will be responsible for 50% of the IP addresses in the scope, and client computers will contact the DHCP servers in turn. In other words, the first client will contact the first DHCP server, and the second client will contact the second DHCP server. The third client will contact the first server, and the fourth client the second server, so on and so forth. Of course, you are free to amend the 50-50 ratio so that one partner receives the bulk of the workload if you wish. Let's take a closer look at how load balancing mode works. Imagine that you have two DHCP servers with a failover relationship. The failover mode is load balancing mode with a 50-50 workload distribution. As long as both partners are available, they will operate in what is called the normal state. When a client computer is first switched on, it will attempt to locate a DHCP server by sending out a broadcast called a DHCP Discover packet. This packet is sent to both DHCP servers. In this example, the first DHCP server will respond to the client by sending a DHCP offer packet offering an IP address. The client will accept the offer by sending back a DHCP request packet. Finally, the DHCP server will lease the IP address to the client in a special packet called a DHCP ACK. To ensure that the second DHCP server is aware of this lease, the first DHCP server will then send a binding update packet to its partner. To acknowledge that it has received the update, DHCP Server 2 will respond with a binding update acknowledgement packet. The two servers are now replicated. Since the workload is distributed on a 50-50 basis, when the next client computer comes along, it will be DHCP Server 2 that responds, and the process is repeated. This remains the case as long as both partner servers remain up and running. So, what happens if one of the DHCP servers were to fail? Let's say that DHCP Server 1 has failed. When DHCP Server 2 next attempts to contact DHCP Server 1, it will not get a reply. When this happens, DHCP Server 2 will drop the connection and will enter what is called the connection interrupted state. At this point, DHCP Server 2 will start handling all of the lease requests from clients, whilst at regular intervals attempting to re-establish its connection with DHCP Server 1. Whilst in the connection interrupted state, if a client needs to renew its IP address lease, it will send a DHCP request packet to DHCP Server 2. And DHCP Server 2 will respond with a DHCP ACK packet renewing the lease. However, if a new client computer were to join the network, DHCP Server 2 will lease out one of the IP addresses that it is responsible for. It cannot lease IP addresses that DHCP Server 1 is usually responsible for, since it does not have control of the entire range. So, when will DHCP Server 2 assume control of the entire range? When DHCP Server 2 enters the connection interrupted state, a countdown is started, called the state switchover interval. The state switchover interval dictates the amount of time which must pass before the server transitions from the connection interrupted state to the partner down state. The length of the state switchover interval can be configured by the administrator. When the server enters the partner down state, another countdown starts, called the maximum client lead time. Again, the length of this can be configured by an administrator. When the maximum client lead time expires, DHCP Server 2 will assume control of the entire IP address range, including the IP addresses that DHCP 1 was initially responsible for. When DHCP Server 1 comes back online, it will re-establish its connection with DHCP Server 2. When the connection is re-established, both servers will return to the normal state. Immediately, the server will request all updates to DHCP that it is not aware of by sending an update request packet to its partner. Upon receiving this packet, DHCP Server 2 will respond with an update done packet containing all the changes. The two servers are once again replicated and will resume the 50-50 workload distribution. The second mode is hot standby mode. Hot standby mode is in many ways the opposite to load balancing mode. With hot standby mode, one of the partner servers is dubbed the active server, whilst the second partner is known as the standby server. The active server is, by itself, solely responsible for leasing IP addresses to clients. In other words, every client computer that requires an IP address will contact the active server. In short, the active server is doing all the work. When the active server gives out an IP address, it will update the standby server by replicating the changes. Understand, the standby server is merely meant as a backup in case the active server fails. That is, if the active server were to fail, the standby server will assume responsibility for DHCP until the active server comes back online. That being said, although the active server is the only server leasing IP addresses, it does not have control of all the IP addresses in the range. By default, the active server is given responsibility for 95% of the IP addresses. Meanwhile, the standby server is given charge of the remaining 5%. This is called a reserve percentage. Of course, it is possible to amend the reserve percentage if you wish. To better understand hot standby mode, let's take a closer look at how it works. Let's consider the same two DHCP servers with a failover relationship. Only this time, the failover mode is hot standby mode. DHCP server 1 is the active server, which means that, by default, it has control of 95% of the IP addresses. DHCP server 2 is the standby server, with a reserve percentage of 5%. Since both servers are available, they are both in the normal state. When a client computer is powered on, it will attempt to locate a DHCP server by sending out its usual broadcast packet. As it is a broadcast, the packet is sent to both DHCP servers. However, since the failover relationship is in hot standby mode, and since DHCP server 1 is the active server, it is the only one to respond. DHCP server 1 will send a DHCP offer packet offering the client an IP address. The client will accept the offer and send back its usual DHCP request packet. Finally, the active server will lease the IP address to the client using a DHCP ACK packet. Even though the standby server is not actually leasing IP addresses, it is still informed of the leases made by the active server in case it has to take over. After completing a lease, the active server will send a binding update packet to the standby server. The standby server will acknowledge receipt of this packet by replying with a binding update acknowledgement packet. The two servers are now replicated. Now, let's consider what happens if the active server were to fail. When the standby server next attempts to contact the active server, it will not get a reply. When this happens, the standby server will drop the connection and will enter the connection interrupted state. After entering the connection interrupted state, the standby server will become the active server. Since DHCP server 2 is now the active server, it will start to handle all lease requests from clients. It will also, at regular intervals, attempt to re-establish its connection with DHCP server 1. Whilst in the connection interrupted state, if a client needs to renew its IP address lease, it will send a DHCP request packet to DHCP server 2. And DHCP server 2 will respond with a DHCP ACK packet renewing the lease. However, if a new client computer were to join the network, DHCP server 2 will lease out one of the IP addresses from its reserve percentage. It cannot lease IP addresses that DHCP server 1 is usually responsible for, since it does not have control of the entire range. So, when will DHCP Server 2 assume control of the entire range? When DHCP Server 2 enters the connection interrupted state, the state switchover interval again starts to count down. When the state switchover interval countdown completes, the server transitions from the connection interrupted state to the partner down state. Whilst in the partner down state, the maximum client lead time begins its countdown. When the maximum client lead time expires, DHCP Server 2 will assume control of the entire IP address range, including the IP addresses that DHCP Server 1 was responsible for. When DHCP Server 1 comes back online, it will re-establish its connection with DHCP Server 2. When the connection is re-established, both servers will return to the normal state. DHCP Server 1 will, once again, become the active server, and DHCP Server 2 will return to its original standby mode. Immediately, DHCP Server 1 will request any updates to DHCP that it is not aware of by sending an update request packet to DHCP Server 2. Upon receiving this packet, DHCP Server 2 will respond with an update done packet, which contains all the updates. The two servers are once again replicated. Now that we know what DHCP Failover is, how to implement it, and how it works, I will now demonstrate how to set up and configure DHCP Failover. To show you how DHCP Failover works, I will, in my lab environment, use two Windows Server 2012 R2 servers, named Server 1 and Server 2. As per the requirements for DHCP Failover, I will configure both servers with a static IP address of 192.168.1.1 and 192.168.1.2, and a subnet mask of 255.255.255.0. I will also deploy two Windows 8.1 Pro client computers named Client 1 and Client 2. Both clients will be configured to use DHCP to obtain their IP addresses. All of these computers will be connected using Ethernet cables and a switch. Since DHCP Failover is most commonly used in a domain infrastructure, I have already installed the Active Directory and DNS roles onto both of my servers. I have also promoted both servers to domain controllers and added both clients to the domain, which is named techtipsfromwill.co.uk. I will start the lab by installing the DHCP server role onto both servers. I will then create a scope and configure a failover relationship. Without further ado, I will now change over to my Server 1 computer. As you can see, the hostname for this server is Server 1, and its static IP address is 192.168.1.1. First, I will open Server Manager. In the top left corner, you can see that the Active Directory and DNS roles are already installed on this server. DHCP is not yet installed. If it were, it would be listed here. To install the DHCP server role, click Manage and select Add Roles and Features from the drop-down list. This will open the Add Roles and Features wizard. From here, simply next your way through the wizard until you arrive at the Select Server Roles screen. From the list of server roles, tick the checkbox for DHCP Server. If you receive a prompt to add further features required for DHCP Server, just click the Add Features button. Once complete, Next your way through the wizard until you arrive at the Confirm Installation Selections page. Personally, I like to tick the Restart the destination server automatically if required checkbox when installing roles or features. Whether or not you tick this checkbox is up to you. When you are ready to continue, click the Install button. It should take no more than a couple of minutes to install the role. Once the installation is complete, you will be notified. If I close out of the wizard and return to Server Manager, you can see that the DHCP server role is now listed, proving that it is installed. Now that the role is installed, the next step is to authorize the DHCP server in Active Directory. Until the DHCP server is authorized, it cannot issue IP addresses. Notice in the top right corner of Server Manager, I have an amber warning symbol. If I click on this symbol, you can see that I still have to complete some post-deployment configurations. To do this, I will click the Complete DHCP Configuration link. This will open the DHCP post-install configuration wizard. To authorize the DHCP server, click Next and then Commit. After a short wait, I will receive confirmation that the DHCP server is authorized and that the post-install tasks are done, so I will close the post-install configuration wizard. Although I have used Server Manager to install and authorize DHCP, it is also possible to do this using Windows PowerShell. Since DHCP Failover requires 2 servers to work, I will now change over to my Server 2 computer to demonstrate how to install DHCP using PowerShell. As per the diagram I showed you earlier, you can see that this is my Server 2 server, which has a static IP address of 192.168.1.2. If I open Server Manager, you can see that, once again, only Active Directory and DNS are currently installed. To install DHCP on this server, I will open a Windows PowerShell prompt. Since I am using Windows Server 2012 R2, I will issue the commandlet add Windows feature. If you are using Windows Server 2012, you will have to use the install Windows feature commandlet instead. Next, I will add the name switch and DHCP, followed by the include management tools switch, which will ensure that the DHCP management console is installed along with the role. Finally, I will add the restart switch. This will ensure that the server is rebooted if necessary. When I run the command, the installation will start. This should take no more than a couple of minutes to complete. Once the role is installed, you will be notified. I will now close Windows PowerShell and reopen Server Manager. Sure enough, you can see that the DHCP role is now installed, but there is still the matter of authorizing the server. To do this, I will reopen Windows PowerShell and will run the commandlet add DHCP server in DC, followed by the name of this DHCP server, which in my case is Server 2, and followed by the IP address of this server, which is 192.168.1.2. When I run the command, the server will be authorized. The DHCP server role is now installed onto both Server 1 and Server 2. The next step is to create a scope. A scope is simply the range of IP addresses that DHCP servers will give out to client computers. In my case, I will create a scope of 192.168.1.101 to 192.168.1.200, a total of 100 IP addresses. Since the scope will be configured for failover, it really does not matter which DHCP server you create the scope on. I will now change back to my Server 1 computer to create the scope. Scopes are traditionally created in the DHCP Management Console. To get there, first open Server Manager, then select Tools and DHCP from the drop-down list. This will open the DHCP Management Console. In the left pane, you can see this DHCP server, server1.techtipsfromwill.co.uk, listed. If I expand the server, I can create either an IPv4 or IPv6 scope. Remember, DHCP Failover can only be configured for IPv4 scopes. To create a scope, right-click on IPv4 and select New Scope from the drop-down list. This opens the New Scope wizard. From here, click the Next button. For DHCP in Windows, a scope has to be given a name to identify it. For now, I will simply call this Scope 1. Optionally, you can also add a description. When finished, click the Next button. Next, you have to create an IP address range. The IP address range is essentially the pool of IP addresses that can be assigned to client computers. To create an IP address range, you have to enter a start IP address and an end IP address. Understand that all IP addresses in between the start and end IP addresses are also included in the scope. For instance, if I enter a start IP address of 192.168.1.101 and an end IP address of 192.168.1.200, this will give me a total of 100 IP addresses in my scope. Further down, you can also set up the subnet mask that will be assigned to all client computers along with their IP address. By default, Windows will attempt to assign a subnet mask of 255.255.255.0. Since this is only a small lab environment, I will leave this on the default. On very large networks, though, you may wish to change this. When you are ready to continue, click the Next button. The next screen allows you to configure exclusions for your scope. An exclusion is an IP address that falls within the IP address range you defined on the previous screen that you do not want DHCP to hand out. In other words, the IP address is excluded and will not be assigned to clients. For instance, if I wanted to ensure that the IP address 192.168.1.101, which falls within my scope, is not assigned to clients, I can add this as an exclusion. In my case, the end result is that out of the 100 IP addresses in my scope, only 99 of them can now be leased. When you are ready to continue, click the Next button. Next, we can configure the lease duration. The lease duration is the amount of time a client computer can keep the IP address it has leased before it needs to be renewed. The default lease duration for DHCP in Windows is 8 days. However, you can change this if you wish. For now, I will leave this on the default and will click the Next button. On the next screen, DHCP will ask whether or not you wish to configure DHCP options. DHCP options allow you to configure additional TCP/IP parameters that will also be assigned to clients, such as a default gateway and which DNS servers to use. Although these options can be configured manually later on, I personally like to do it whilst creating the scope. So I will select the Yes, I want to configure these options now radio button, and will then click the Next button. The first DHCP option is the default gateway. The default gateway is essentially the router that allows this network to communicate with other networks. In a lot of cases, the default gateway will be the router that connects your network to the internet. If you do not supply a default gateway, your client computers will have no way of communicating with computers outside of your network. In highly secure environments, you may wish to leave this blank. To supply a default gateway, simply enter the IP address of the router, which in my case is 192.168.1.254. Click the Add button, and then click the Next button. Next, you have the option to add a domain name and DNS servers. These options are intended to help your clients with name resolution. The parent domain is essentially the domain name that your clients will use. In my case, this is techtipsfromwill.co.uk. Further down, you can specify the DNS servers that clients will use for name resolution on your network. The DNS servers you add here will be used to resolve computer hostnames on your network into IP addresses. Since my Server 1 and Server 2 servers both have the DNS role installed, they can both be used for name resolution. Notice that DHCP has detected that this server, Server 1, is a DNS server and has already added its IP address. Since it is a good practice to have two DNS servers for fault tolerance, I will add Server 2 as an alternative DNS server and will attempt to resolve it. Notice that DHCP has correctly resolved the IP address of Server 2 into 192.168.1.2, which, if you recall, is Server 2's static IP address. So I will add this to the list of DNS servers and click the Next button. The next option is to add a WINS server. WINS is another service that is used for name resolution. However, it is considered a legacy technology and, over the years, has become increasingly deprecated. WINS is used to resolve NetBIOS names into IP addresses. With NetBIOS names generally used less and less nowadays, WINS is only required if you are running some sort of legacy operating system or application on your network that requires it. Since DNS is widely favoured over WINS for name resolution, most modern networks will have no need whatsoever for a WINS server. Nonetheless, you can add the IP address of your WINS server if you have one. Since I have no WINS server on my lab network, I will leave this blank and will click the Next button. On the next screen, you will be asked whether or not you wish to activate the scope. Understand, until the scope is activated, it cannot be used, and DHCP will lease no IP addresses until it is activated. You can think of a scope which hasn't been activated as essentially disabled. Of course, you can activate and deactivate scopes manually at any time. Since I am ready to use my scope, I will select the Yes, I want to activate this scope now radio button, and will then click the next button. To complete the new scope wizard, I will click the Finish button. In the left pane, notice that my scope, Scope 1, has appeared listed. If I select the Address Pool option, you can see my IP address range, as well as the IP address I chose to exclude from the range. Further down, in the Scope options, I can see the additional options I configured, including the default gateway and the DNS servers. The scope is now created, activated, and is ready to use. Now that we have our scope on server 1, the next step is to create the failover relationship between server 1 and server 2. When the failover relationship is established, I will add the scope I just created to the failover relationship in order to replicate it to both partners. So I will now change back to my server 1 computer to demonstrate how to create the failover relationship. To create a failover relationship between two DHCP servers, in the left pane, right-click on the scope you wish to add to the failover relationship and select Configure Failover from the drop-down list. This will open the Configure Failover wizard. On the first page of the wizard, you are asked to choose which scopes to add to the failover relationship. Remember, any scope added to the failover relationship is essentially made highly available. By default, Windows will attempt to add all scopes to the failover relationship. To change this, simply untick the Select All checkbox. This will allow you to pick and choose which scopes to add to the failover relationship. Since I only have one scope to choose, I will leave the Select All checkbox ticked and will click the Next button. On the next page, you are asked to choose a partner server with whom to establish a failover relationship. Remember, you can only have 2 DHCP servers in any failover relationship. To nominate a partner server, simply enter its hostname or fully qualified domain name into the partner server field. In my case, I will enter server2.techtipsfromwill.co.uk. If you are unsure of the hostname for your partner server, you can click the Add Server button to browse the authorized DHCP servers on your network. When you are ready to continue, click the Next button. You are now ready to create the new failover relationship. First, you are required to give the failover relationship a name so that it can be identified. You can do this on the Relationship Name field. In my case, I will name the failover relationship Server 1, Server 2, Failover. Next, you are required to choose a mode. The mode you choose here will determine the behaviour of the failover relationship. From the drop-down list, you can choose either Load Balance or Hot Standby. If you opt for Load Balance mode, which is the default, both of the partner servers will participate in leasing IP addresses to clients. As such, you must configure a load balance percentage for the local server and the partner server. This is essentially how the DHCP workload is distributed between the partner servers. By default, the workload is split 50-50 between the partners. Of course, you can change this if you wish. Alternatively, if you choose Hot Standby mode, you will have to choose which of the partners to make the active server and which to make the standby server. By default, the server you are working on, server 1 in my case, will become the active server, and the partner server, the standby server. Of course, you can change this if you wish, using the Role of Partner Server drop-down list. Further down, we also have the Addresses Reserved for Standby Server setting. This is a percentage of IP addresses from the range which are kept in reserve. These IP addresses are for use by the standby server only, should it have to take over. By default, this is set at 5%, but can be changed if you wish. Personally, I am a fan of load balancing mode, so I will switch this back. The next setting is the state switchover interval. If you recall from earlier, when a server loses communication with its partner, it will change to the connection interrupted state. The state switchover interval determines the amount of time, in minutes, the surviving server will remain in the connection interrupted state before changing to the partner down state. If this checkbox remains cleared, the surviving server will remain in the connection interrupted state indefinitely until an administrator places it into the partner down state manually. Why Microsoft set it this way, I have no idea. If I tick the checkbox, I am able to choose the length of the state switchover interval. Personally, I am a fan of setting this low to speed up the transition. Related to this, we have the maximum client lead time setting. The maximum client lead time setting determines the amount of time a server will remain in the partner down state. When the maximum client lead time expires, a server in the partner down state will assume that its partner isn't coming back online and will therefore assume control of the entire IP address range. Once again, I am a fan of setting this low to speed up the failover. Next, you have the option Enable Message Authentication. When this checkbox is ticked, all communication between the two partner servers is encrypted. If you are concerned with security on your network, keep this option enabled. If you opt to use this feature, Windows will prompt you to enter a shared secret. This is essentially a password used by both partner servers to confirm the other's identity. Of course, it is recommended to follow password best practices and make the shared secret complex. When you are ready to continue, click the Next button. To create the failover relationship, click Finish. Immediately, DHCP will create the failover relationship. To finish the wizard, just click the Close button. The failover relationship has now been created. Assuming it was successful, my scope should also be visible on my Server 2 computer. So I will now change over to Server 2 and take a look. If I open the DHCP Management Console, expand my server2.techtipsfromwill.co.uk server, and expand IPv4, sure enough, you can see my Scope 1 scope, proving that it has, in fact, been replicated from Server 1. To view or change the failover relationship settings, right-click on IPv4 and select Properties from the drop-down list. At the top of the IPv4 Properties dialog box, select the Failover tab. From here, select the failover relationship and click the Edit button. Notice that I can see the state of this server and the state of my partner server. Since both servers are booted and available, they are reporting a status of normal. Further down, I am able to change all of the settings I configured earlier, including the failover mode. For now though, I will leave these settings as is and will cancel out of the Properties screen. DHCP Failover has now been implemented. To prove that the load balancing mode is working correctly, I will now deploy my two Windows 8.1 Pro client computers, Client 1 and Client 2. Since I have set the load balancing ratio on my servers to 50/50, Client 1 should lease its IP address from Server 1. Client 2, on the other hand, should obtain its IP address from Server 2. Without further ado, I will now boot up and change over to my Client 1 computer. As you can see, I am now on my Client 1 computer, which is running Windows 8.1 Pro. To prove to you that this computer is configured for DHCP, I will open the Network and Sharing Center and will view my adapter settings. As you can see, I have just one network interface card installed in this computer. If I open the properties for this adapter and view my IPv4 settings, you can see that this network adapter is set to obtain an IP address automatically and to obtain DNS server addresses automatically, confirming that this computer is indeed set up for DHCP. I will now close the Network and Sharing Center and return to my desktop. Next, I will open a command prompt. From here, I will issue the command ipconfig/all. For my Ethernet network adapter, notice that this computer has received an IP address of 192.168.1.102. If you recall from earlier, I excluded the 192.168.1.101 IP address from my scope, so that it would not be given out. This explains why this computer has received the next available IP address in the range. Also note that the subnet mask is 255.255.255.0 and that the lease period from being obtained to expiring totals 8 days. The default gateway is 192.168.1.254 and the DNS servers are 192.168.1.1 and 192.168.1.2, all exactly as I defined in my scope. One particular setting I would like to point out is the DHCP server setting. This is the computer from which Client 1 is leasing its IP address. As you can see, this is reported as 192.168.1.1, the IP address of my Server 1 computer. As expected, Client 1 has leased its IP address from Server 1. As such, I will now boot up my Client 2 computer and will investigate where it has obtained its IP address from. This is my Client 2 computer. The setup of this computer is practically the same as Client 1. In the Network and Sharing Center, you can see that Client 2 has just one network adapter, which, if I open its properties, is also configured for DHCP. I will now close all windows, open a command prompt, and issue ipconfig/all. On the Ethernet network adapter, you can see that Client 2 has received a totally different IP address of 192.168.1.151. Once again, the rest of the settings are as I defined in the scope. However, notice this time the DHCP server setting is different. 192.168.1.2, the IP address of my Server 2 computer, proving that my DHCP servers truly are load balancing DHCP leases. The final topic I would like to discuss in this tech tip is how to delete a DHCP failover relationship. Let's say that we now want to remove the failover relationship between server 1 and server 2. Of course, it goes without saying that, if you do this, DHCP failover is effectively removed, and the two DHCP servers will no longer replicate scope changes with one another. Another point to bear in mind is that, after you delete the relationship, the scopes that have been added to the relationship are only retained on the server from which you deleted the relationship. For instance, if I were to log onto server 1 and delete the failover relationship, the relationship will immediately go away. Server 1 and server 2 are now effectively two separate DHCP servers. Since I deleted the failover relationship on server 1, the scope is retained on server 1, but is removed from server 2. This makes perfect sense because, if you recall, having two DHCP servers on the same network configured with the same scope is a recipe for disaster. I will now change over to my server 1 computer to delete the failover relationship. Failover relationships can be deleted from within the DHCP management console, so I will start by opening the tool. Once in DHCP, right-click on IPv4 and select Properties from the drop-down list. Next, select the Failover tab. From the list of failover relationships, select the relationship you want to remove and then click the Delete button. You will be prompted to confirm you want to delete the failover relationship and will be reminded that this will delete the scopes on the partner server, which in my case is server 2. To proceed with the deletion, click the OK button. The failover relationship has now been deleted. Notice that, like I said, the DHCP scope is still accessible on server 1, since this was the server from which I deleted the failover relationship. The scope will, however, have been removed from server 2. This concludes this tech tip from Will. I hope you have enjoyed this tech tip and found it informative. If you'd like to see more Windows Server 2012 and Windows Server 2012 R2 training videos, check out our YouTube channel. And remember to support our videos by liking them and by subscribing to our channel. Many thanks, and we'll see you on the next tech tip.